Okay, it is 12:03. It is time to begin. So, good afternoon, everybody. My name is Adrienne Esposito. I'm the Executive Director of Citizens Campaign for the Environment. Thank you so much for joining us for this exciting Lunch and Learn. What we're going to do today is we're going to hear from some fabulous people. We're very excited to have Dr. Luis Medina with us. Dr. Luis Medina is an associate professor for the School of Marine and Atmospheric Scientists at Stony Brook, Science at Stony Brook. He has some groundbreaking research he's going to present on microplastics in the ocean. It's most likely stuff you've never heard before. So we're happy to be able to provide you that. That's going to be followed up by Cynthia Seibold, who is the founder and executive director of Balloon Mission. And also, then we're going to have a panel discussion with the fabulous Rob DiGiovanni, who is the executive director and chief scientist for AMC's, or the Atlantic Marine Conservation Society, as well as Rob Weltner, who's the executive director for Operation Splash. He also likes to be referred to as a professional aquabiologist because he knows more about garbage in the ocean and the waterways than anybody else, I think, on the planet. And Artie Koppelman will agree with me on that, I know. So thank you so much. This is part of a series of lectures and informational sessions that we have been hosting, and we appreciate everyone's time and support on this. But with no delay, I'm going to turn this over to Dr. Luis Medina, as I said, the Associate Professor for School of Marine and Atmospheric Sciences at Stony Brook University. He's going to be doing a PowerPoint, so he'll be sharing his screen with all of you as well. So, Dr. Medina, it's all yours.
Okay, can you see, everyone can see the screen?
That's perfect. Yep. And it's in presentation mode. So it's
Okay. Well, first, thank you very much for the invitation. It's always for me a pleasure to share what I'm doing here at Long Island and in other parts of the world, trying to understand the microplastic pollution, and not only microplastic, but also plastics and marine debris, um, and share with the people that at the end is the most important thing for us. So today I'm going to talk about identification, distribution, and source assessment of microplastic around Long Island. I'm gonna talk about I think 4 different projects. Some projects are done, and other projects are right now being developed. So I'm gonna try to go all over this. Okay, first I just want to start with this very basic. What are plastics? Plastics are synthetic polymers. Polymers are big molecules, basically macromolecules that we know. So if you think about a carbohydrate, if you think about sugars, if you think about lipids, those are polymers. Those are macromolecules. So the meaning is just huge molecules that we have in our bodies. But also we can make those macromolecules, those polymers. So plastic are synthetic polymers or are man-made. So these polymers are made by these monomers. So we have here 3 examples of polystyrene, polypropylene, and PVC, the respective monomers that make those big macromolecules. So, but why are we so much in love of plastic? Why our society use that much plastic? And the reason is because they are light. So they are light and strong. They can be molded in any shape, so we can build anything basically on plastic. They are water and shock resistant. And at the end, they are cheap to make, and they can be produced in mass. So that's the main reason that we use so much plastic, because they're cheap and we can produce a lot of those polymers to make a lot of things. So you can see here an example of how we use plastic, how plastic is in all our life, in all the industry, entertainment, health. In every part of our life, plastic is involved. So plastic production since 1950 is had been 83,000 millions of metric tons. That is a lot of plastic. Half of that production had been discarded to the environment, around 5,000 million metric tons. And what's happened when this plastic is discarded to the environment, basically it goes everywhere. It reaches our river, it reaches our beach, it reaches the open ocean. So you can see here different part of the world, Southern Ocean, this is Antarctic, South Caribbean, this is where I am from. I'm from Venezuela, so these are pictures taken by me. South Pacific, the Red Sea, Philippines, Pacific Ocean. So these are pictures of plastic everywhere. So you can see here when we talk about the garbage island, I'm pretty sure you heard about this in the news. Garbage island, these are two main in the Pacific Ocean, but we also have this garbage island in the Atlantic Ocean. So we can have the garbage island in the coast of California or away in the middle between Hawaii and the coast of California. These are not islands like we know that an island is. It's just accumulation zones. These are areas in the ocean where a lot of plastic accumulate, and not only plastic, also other marine debris. So once they reach those areas, they can, for example, sink, and this bigger piece of plastic goes through the process of fragmentation. So fragmentation can occur in two ways: biological fragmentation and physical fragmentation. Biological fragmentation means like organisms like bacteria break down the plastics, producing small pieces of plastics in the ocean, in the water. Physical fragmentation is due to the wave, basically. UV radiation, when the sun hit the plastic, that energy is going to change the molecules in the polymer, affecting the polymer physically and chemically. So that's when if you touch an old summer chair that you have in your house for years, and you touch that old summer chair, you're going to feel those small grains in your hands. That is fragmentation due to the UV light, to the sun. So that is a way to produce from one big piece of plastic, like the summer chair, millions and millions of microplastics. So when we talk about microplastics, we're talking about particles that are less than 5 millimeter in size. So just for comparison, you can see here the red square is 5 millimeter, and just to compare 1 inch. So anything that fall into this red square, that's we call microplastics. So you can see that can go from 1 micrometer, the size of the bacteria, to the size of a toy, basically. So microplastic can be primary or secondary. Secondary are these one that I just talked about, fragmentation, pieces of plastic that come from the fragmentation process, or can be produced intentionally by the industry. So those pellets that we put into some healthcare products. So that's why a study of microplastic is so challenging, because you are facing particles that are diverse in terms of shape, size, color, and chemical composition. So you can see here different shapes and colors of different microplastic that we found in the beach. So what are our analytical approach or our methodology to study microplastic here at SOMAS or in my lab? Well, we first go on sampling. We go to the ocean, to the bay, we take water samples or wherever we're trying to measure. So we extract those plastic from the water. We clean up the water doing digesting processes, for example, using hydrogen peroxide to get rid of a lot of organic matter that is in the water. If you think about coastal water, there is a lot of things there, from phytoplankton to zooplankton to organic matter. So in order to better detect these small particles, it's better if you clean somehow your samples. So then we concentrate these particles in a filter. So we filter our water through a special filters, and then we take that filter with everything that is collecting that filter from that water, we take to our analytical techniques. So we basically use vibrational spectrometry, and we use two techniques here at SOMAS. In my lab, we had a Raman microspectroscopy, and we had optical photothermal infrared. Both of them use a source of energy, which is a laser, and that laser is going to interact with the material that we are trying to identify, and that interaction is going to create a feedback to the instrument, so we can identify specific materials that made those polymers or other particles. So I'm gonna just very quick show you the two approaches that we use here. So imagine that we filter all our water is on our filter. So you see the filter there. That very circle thing is a filter after filtration. So you can see a lot of things in that filter. But basically, we cannot say what is in that filter. Just a simple view, we cannot say. There is a lot of things there, even when after we clean it. So this is a mosaic image. So we took around 100 small images that are those square, and we create this mosaic of a 13 millimeter filter. So this is a very small filter. And what we try to do in this approach using Raman is we try to identify whatever is in those red square. So those are for reference, those are not the real square. We try to do around 40 of these square around the filter, and basically we go there and try to detect the particles. We don't know where the particles are, but we go there, and you can see here in the small square is a representation of this, and then we can detect using Raman very, very small particles, 1 micrometers to 50 micrometers. And each of these colors are different materials of that particles. This is a particle that we detect there. So we can find, for example, quartz, polyethylene, and this is silica. So in these particles, we found polyethylene, that is a polymer, it's a common plastic. And then we use statistics and mathematics to try to extrapolate whatever we found there to our volume of water. So that is one approach. The other approach that we're using now, we're investigating this more, is collocated OPTR, optical photothermal infrared, with fluorescent microscopy. So in this approach, what we are trying to do is stain the particles so the particles tell us where they are in the filter. So we don't need to go and try to detect them, spending a lot of time there. So we use Nile red, which is a stain technique. It create very beautiful fluorescent imaging, like the one that I'm going to show you now. So this is a filter in a normal view. So this is the same filter after we stain it with Nile red, and all those things that you're seeing there are particles that attach that Nile red, that stain, and now are fluorescent. So now we can go there to wherever the particles are in the filter and investigate what are they. So we can go image by image. So we can produce this a small image and go to those specific and interrogate one of those particles. So for example, in this filter, we have found polyethylene terephthalate, which is PET. This is the polymer that our water bottle are made of. We also detect nylon, which is the second one here, but also polypropylene, which are the polymer that the lids of the Pepsi or Coca-Cola bottles are made of. We also collect polyethylene. So this is a faster approach because we don't need to interrogate the field. We just go where the particles are. But I have to say, not all of those particles are plastics. Some of them are lipids or other materials. But even though with this approach is so much faster, and we are in the process of be more efficient in this technique. So this is going to help us a lot to expand our analytical methodology. So after that, this is we can detect the number of particles in the water, and then we can say, well, there is amount of particles in 1 liter of water. Also, we can measure the size of the particles, and knowing the identity of the polymer, we can know the density, and knowing the volume, we can calculate the mass. So we have number of particles and mass of those particles, which is very important when you want to relate the concentration of microplastic in the ocean with what the amount of plastic that is produced by the industry. When you want to create budgets of plastics, when you want to compare this number of plastic with with the industry, what it's doing. So making budget in mass is very, very important. So I'm going to talk about today about 4 projects that we are now conducting in Long Island. The first one is microplastic in the New York Bay. So these data have been already published in Marine Pollution Bulletin. So in this paper, we did the Caribbean, we did the Arctic, and we also did Long Island. And the cool thing about the part of Long Island, this is the south shore of Long Island, 9 station that you can see here. You can see here this Fire Island, we collect surface water from the nine station, and this was part of a study that conducted SOMAS a few years ago, trying to understand water quality near the Southwest Sewer District outfall discharge. So now station number 6 here is where the outfall discharge the water from the sewer plant. So in that study, they collect water around that discharge. So we took advantage of that and we analyzed looking for plastics in this area. So first, what I'm going to show you here, imagine in this plot that you are looking at the ocean from above. So you are in the sky. So the gray part is the coastal, the beach. So these are the station, each one of those points. So you are looking at the ocean from above. Like imagine that you are in a helicopter. So red colors are more abundant than blue colors. So in average, in that area, we collect around 40,000 particles per liter of microplastics in average, being the most abundant in station number 1, which is here in your left panel, the red point. We collect there around 95,000 particles of microplastics. And then the minimum was around station 9, and we collect 13,000 particles per liter in that area. That is equivalent around to 18 micrograms with a maximum 61 and a minimum 0.42. So you can think about this mass being like, oh, but it's not that much. But if you think about the trophic levels and you think about the food web, this amount of plastic have a lot of implication in our trophic web. What is eating this plastic? What is transferring this plastic for the lower levels to the high levels to us when we eat fish, for example? So
Louis, were you surprised by those results?
uh, I, I was surprised that we didn't find more. Being in the outfall discharge, but this is a very dynamic area with a lot of current, and I think particles move very fast from this. And you can see here in the panels, these blue arrows show the currents that are predominant in this area. And you see the red colors more abundant are to the west of the outfall discharge. So what we think is happening is particles are being moved by the current, surface current to the west very fast. We don't see that pattern in the mass, but it's because the mass is dependent on the density of the polymer and the size of the particles. So if you have one bigger particle, like in this case, 20 micrometers, that can influence the mass that you are seeing there. And another important thing here is that the abundance of these small particles are 100 or 1,000-fold higher than the microplastic captured by plankton nets, which is our traditional method, our traditional way to study microplastics in the ocean. So smaller particles are more abundant than bigger particles, and we know now that. So these are particles around 1 micrometers. We don't know what's happening in the nanoparticle fraction. So these are even smaller than the thing that we're talking about here. So this is in the upper panel, you can see a size distribution of the particles. So this is an histogram showing you in the x-axis is the diameter of those particles, and in the y-axis is the relative abundance. So you can see the particles smaller than 5 micrometer are more abundant than bigger particles. So that is telling us that these small particles are very abundant. So the other thing that I want to show you for the study is the diversity of the polymer that we found. We found polystyrene, polypropylene, polyethylene terephthalate, PET, polyethylene, and Teflon. Also, we found this synthetic pigment, phthalocyanine. It's very weird to pronounce, but this is a pigment we found this pigment everywhere. Not only us, different studies, it's in the sediment, in the water, in organisms. So this is a pigment that is used, for example, in the maritime industry to paint boats. That blue color that you see in the boat is basically this pigment. So we found this pigment everywhere, not only here in the Caribbean, in the Arctic, and it's been reported by other researchers. So this is a very common pigment. Okay, so the second project that I want to talk about is microplastic identification, distribution, and source of microplastic in the Peconic estuary. This project has been carried together with the Peconic Estuary Partnership. Again, I'm going to show you preliminary results. This is not done yet. We are in the process of measuring all this station. So we collect samples in August 2024 and April 2025, and the main objective of this project was to see if there were seasonal changes in the concentration of microplastic in the Peconic Bay. Seasonal changes in the term in August, the tourists were carrying on more microplastics. In April, if the rain and the river discharge is putting more microplastics in the bay. So we want to compare these two contrasting seasons there. So we collect, we did this together with the Suffolk County Department of Health Services. We went with them in their surveys. They were very helpful for us. So we went to different parts of the Peconic Bay. I'm going to show you here. We collect samples in 20 stations or 19 stations from the river, in Riverhead, to the almost the open ocean here to the east. So we divide the bay in two areas just for logistics because it was more simple to sample the bay in that way. So we collect discrete water samples that we call only using glass bottles, but also we collect net toll samples. And we want to see the difference between those small the abundance of the small particles and the big particles. So we collect net tolls in all these transects that you can see here, together with our discrete water samples. So what we found again is that particles smaller than 6 or 5 micrometer are more abundant than bigger particles in our discrete water samples, in our bottle samples. You can see here that most of the particles are between 1 and 5 or 6 micrometers in diameter. And also in this lower plot of the panel, it's just showing you that the small particles here are more abundant than the bigger particles. So that's just confirming us statistically that this is true, this is happening. This is how microplastic distribution or microplastic were distributed around across the bay. So in average, we have 12,000 particles per liter with a maximum of 50,000 particles per liter in station 11 here. So basically, we don't see a gradient that what we're expecting from the river to the open ocean. What we see is more like accumulation areas. So there is a specific point where microplastics accumulate. It's not like a specific source of these microplastics in the bay. And these are the smaller, the 300 micrometers. So as a reminder, again, we are in the process of finishing this project. But I just want to remind you that in Peconic Bay, there is a lot of oyster and other organic farming there. And there is a discussion about what are the implication of this in the Peconic Bay and other bays. We have, for example, no detectable microplastic in station 7 and 8. And this is the distribution of the bigger particles with the net toll. So in this case, we see a pattern here from the river to the open ocean here. So more particles in the head, in the discharge of the riverhead, in riverhead, and then small abundance going out of the ocean. So in the big particles, we saw that distribution. One of the things that I want to show you here is the particles that we found that we collect with the net tolls. We collect these red fibers in almost each one of the stations that we measure, and it's not contamination of our method. It's nothing that we are carrying on. It's just things that were in the water. So you can see the fibers are the same, and they are all around the Peconic. They are polypropylene, and we identify the polymer. They are polypropylene, and they are more abundant in some of the stations than others. But we collect all these red fibers in August, I have to say. But also we collect polypropylene, polyestyrene with these samples and PET. So this is very interesting, but I have to say the abundance of this is very low. The maximum abundance was 20 particles per liter, and that go back down to 1 particles per liter in this size fraction. So the abundance are totally different. And the polymers are, again, polyethylene, polyestyrene, polypropylene, PVC, and those pigments that I mentioned before. I have to say, related to the chemical identification of the polymer is what we are finding in the water is those polymers that are very common in the production. So the most common polymer that we produce and that we use is the one that we're finding in the plastic. Polyethylene again, polystyrene, polypropylene, PET, PVC. Those are the polymers that we found in the water. The other project that I want to mention in these two last projects we are working on this right now is marine debris in the South Shore. Where you're seeing here is Jones Beach in the figure here. This is Lido Beach, Lido Boulevard from Long Beach to Point Lookout in the South Shore. I collect sample in this corner of Point Lookout here. 1 year of observation. This is marine debris that I collect in the beach. I follow NOAA marine debris protocols to do this. I did bi-weekly samples, so I have 26 sample events in that year, beginning in October 2024 and finishing in October 2025. Debris from 0.3 millimeters to macro debris, high temporal resolution, and this includes sampling following the Hurricane Erie in August 2025. So I've been finding a lot of interesting things. This is the area of the Point Lookout here. It's inside, and this is the area that we collect the samples. So these are some of the samples that we collect. These are the plastic, the samples of each event. So we already cleaned them, and they are ready to process. In fact, right now I have a student in the lab in the next door working in these samples, measuring them, identify them chemically, and try to assess the sources of these particles. So this is particles, microplastic, basically after the Hurricane Erie. So one interesting thing that we saw after the hurricane, and I'm going to mention because this is a sample that we processed already. I just want to show you this plot. This is the sample event, the date, and the weight of all the things that we found there. I will not take this with a lot of detail because it's not done yet. And this is mass. This is the weight. Of course, if you collect 1,000 small particles of plastic, they're going to weigh less than just a glass container. So in terms of mass, there's going to be difference there. So we are trying to figure out how is the way best to report, the best way to report all these findings. But these are some of the things that we found there. We found shotgun case. We found a lot of artificial baits that is using for fishing, those type of things, and try to relate it to the activities that's happening in that area of the bay. With this, what we want to do at the end is this high frequency sampling. We want to detect temporal variability. We quantify the storm driven pulse like the Hurricane Erie. So after the hurricane, and that was the only sample event that we collect these pellets that you're seeing here. And these pellets are the one, if you want buy plastic from a company, these are the pellets that they sell to you to make toys, to make whatever you want to do. So these pellets are produced by the industry, and that's what the only time that we found these pellets in that specific beach. We want to estimate annual debris flux, building predictive models to see how much of debris are going to the ocean, and support coastal management. And one of the things here is very different, on my experience here, it's very different to go and sample in this day, in the picture with my dog. You see the dog running there. It's very different to sample here in that with these characteristics on the beach than sample in the next photo with all the algae. So try to determine where is the best time to go for example, to do cleaning, to take the community out there and do cleaning survey or beach cleaning. So those are the things that we want to get of this project. Also, marine fauna associated with this debris. We found a lot of animals associated with this. And from there, we can, for example, determine resident time of particles in the bay, because we know they're growing in the plastic. For example, some animals growing in the plastic. So knowing the growth rate of these animals, we can determine how much that particle spend in the water in the bay. So that is some of the things that we want to do with this. Uh, and finally, this is the last slide. This is the last project that we are doing right now with my PhD student. It's micro nanoplastic entering into the Hudson River planktonic food web. So for this, we wanted to do the historical revelation from a long-term environmental monitoring program. This is the Hudson River Biological Monitoring Program. If you don't know about this program was established after the Indian Point nuclear plant was established in the Hudson River to try to monitor, to see the impacts of that plant across the Hudson River. So it goes from 1970 to, I think they're still going, they're still sampling. And basically they sample fish and water quality across the Hudson from uh, upriver to Battery Bay to Battery Point in New York City. So what the idea here, my idea was, okay, let's go to fish on 19, they were caught in 1970 and see how's the difference in ingestion of plastic to fish that are being caught in now. So this collection was donated to Stony Brook, and right now you can see these boxes in this warehouse in Port Jefferson are full of jars of fish. So we are getting fish from three different species. So we are dissect them, taking the stomach, taking the gills, the flesh, and we're trying to see the difference between ingesting plastic from our fish. This one is 2007. You can see here, 2007, and we have been found plastics here. So this is very interesting. Here, this what you're seeing here in this picture, in the bottom picture, is a shrimp that was in the stomach of this small tomcat. So the stomach was full. We opened it, and the shrimp was there intact, was perfectly preserved. So when we opened the stomach, the shrimp was perfectly preserved. So what we think, or what I think, is just the fish ate that shrimp, and 1 minute later was caught by the net because the shrimp was intact. You could see everything, and you can see here that small particle there. Uh, that was polyethylene. We identified as a polyethylene in that fish stomach from 2007. So the idea is to compare different years and see if there is changing in the ingestion of plastic of all of this. And now that's it. I just want to thank you again. This is what we do is to the science and get good data, get conclusion, and communicate that to the people, and to try to make better policies or try to make policy based on science. And thank you, everyone. If you have any questions.
Okay, great. Thank you. We're going to take questions after our next speaker, but that was terrific. And there are several questions in the chat, so please look at them, Louis, before we begin the panel discussion.
Okay.
But we're going to move on to Cynthia Seibold, who again is the founder and executive director of Balloon Mission. We like to say, you know, when you release those balloons because you think they're going to heaven, they're not. But they are sending wildlife there prematurely. So Cynthia is going to talk a little bit about that.
Thank you so much, Adrian. So this first picture that we're seeing is from Operation Splash. This is where our balloons are ending up here on Long Island. They're also in the waters and on our beaches. And Balloon Mission, we're looking to reduce this type of specific plastic pollution, and we're on a mission to prevent balloon litter. Next slide, please. Why is a balloon mission needed? Stupid is as stupid does. You know, not all balloons end up that we are finding are from intentional balloon releases. We have real good intentioned people who don't want to pay for a delivery fee, who are cramming 200 balloons into their vehicles and driving off with them wrapped around the car. I have another slide. Next slide, Jordan. This is a windy day coming out of Party City. This gentleman was, this was a Facebook video, and you could see he's trying to get the balloons. He's fighting the wind. This is a little known but widespread problem. Intentional balloon releases, it's estimated about 1 million balloons are released for memorials and celebrations in the United States every year, but we also have these accidental releases. And I stop and wonder, is it lack of awareness? Is it carelessness? balloon mission is needed because we need to educate people about it. The unintended environmental harm that happens when balloons fly in the sky, and also promote safe practices within the balloon industry. When you're coming out in both these situations, the balloon decor in the first slide should have been delivered. These balloons here should have been bagged and weighted down. These are all preventable problems. Next slide. Next slide, Jordan. These balloons, oh, I'm sorry, one more back. The balloons here were found on the side of the Meadowbrook Parkway. It was a 24 air-filled mat, and we know it's air-filled because it wasn't floating away. And then on the right side was the Wantua Parkway. There were 16 balloons there, and they were both latex and foil. These are 2 graduation balloons that were found on the side of the salt marshes, and both of these, March and June of this year. Whenever I go out, I am stopping my car and finding balloons and pulling over to get those balloons. As is many of you, I know Rob Weltner is one of those warriors who's out there pulling those balloons off the side of the road. Next slide. There we go. So where are we finding balloons? This is actually, I'm gonna show you an actual balloon litter survey that we're doing here on Long Island at West End 2 and Jones Beach. I am a member of the Mid-Atlantic Regional Council on the Ocean. I'm on the Marine Debris Work Group, and I have participated in balloon litter surveys from 2022 on. And these are 14 surveys that have happened here, and we've collected 2,363 balloon materials. I love the Marco portal. You can scan the QR code to find all sorts of I geek out over this. But where else are balloons being found? Next slide. We have informal balloon litter data, not the formal kind that we just saw, but these are where we're finding some of the balloons here on Long Island. Atlantic Marine Conservation Society, they've done their beach cleanups and have pulled over 1,700 balloons. Operation Splash between 2021 and 2025, over 9,000. We have also Callahan's Beach. We have a balloon mission volunteer out in Fort Salonga who just in 2026 has documented in 72 days 142 balloons. Next slide, please. Our balloon mission is a world without harmful balloon litter. We are looking to educate about this little known but widespread problem, and stop intentional balloon releases, but also educate about responsible balloon practices. With our innovative, sustainable solutions and a collaborative approach to change, we're engaging the industry, the public, and lawmakers to bring an end to this type of plastic litter. Next slide. We have our strategic pillars. The only one I'm going to talk about today is public awareness and engagement and how we operate. Next slide. This is our balloon collection bin, and I'm super proud of this. This was designed by the Long Island Children's Museum. For us, you know immediately when you see this, we are collecting balloons. We have these in public. It's a permanent structure in public places. We want it to be visible. We partner with libraries. We partner with schools, our environmental groups. We're getting the message about responsible balloon practices. And another way we're messaging, we work with the New York State DEC, Town of Babylon, all of our groups and partners who, when they're going out, AMCs, when Allie and when Ellie and Mickey are doing their presentations and we're not there to do our own, they're sharing balloon mission. And so we have teachers and scout troops reaching out to us because they heard about balloon mission at Fire Island in a brochure. So we're very excited at some of the partners who we've had over 100 organizations say yes to our program. We just had elementary school in Massapequa call us up. We've collected balloons. We had no idea they were doing it. Sure, we're happy to come and pick up your balloons. This is for post-event balloons. They're the clean ones. So once the fun is done, you pop and drop your balloons into our balloon bins. Next slide, please. These are our metrics. In 3.5 years, we have collected almost 83,000 balloon materials from all across Long Island. And what does this show? This shows that even around something so silly as a balloon, people are looking for change. They're looking for solutions. They are looking to be part of a solution. The two things can be true. You can enjoy balloons and be responsible with them. Next slide, please. This is a pop and drop in action at the Long Island Children's Museum. Long Island Children's Museum has one balloon bin in their lobby for public drop-off, which is seen by over 300,000 people every year. And then, yes, once the fun is done, you pop and drop your balloons into our balloon bins. We see them safely disposed of. Next slide, please. This is some education. This is our tabling event. We were there for STEM weekend. We show impact of the unintended harm of balloons in our environment. We should give alternatives, eco-friendly alternatives to intentional balloon releases. And then we have a pledge. You sign your name on a sticky note that you pledge not to release balloons into the environment. Next slide, please. These are our balloons going to ReWorld. Covanta was one of our first partners. Maureen Early is there on the left. She has been our biggest supporter through this whole initiative, and she has helped make Balloon Mission possible. Our motto is collect, protect, preserve. We collect balloons to protect animals and wildlife and preserve our environment and our waters. Next slide. How are we getting the message out about responsible balloon practices? We offer our permanent balloon bins and sometimes if you can't have a balloon bin, if we're selling our balloon bins, just slap out a cardboard box, call us up, let us know you're collecting balloons. Signs are also a very big part of education. In 2019, all the good people on this call, Citizens Campaign for the Environment, Splash, AMC's, Surfrider, all got together with the municipalities and said, hey, we need to prevent intentional balloon releases. And in 2019, these laws were passed, but nobody knew about them. And so when we came along and I'm like, why are we still seeing balloons? We need to get signs up. So this is Girl Scout Troops 1416. They chose Balloon Mission, and we put 8 balloon signs, no balloon release signs, out in Southold. We also, next slide, please, have balloon signs in the town of Hempstead, in Long Island State Parks, in the city of Long Beach. So I think it's about 62 total signs up that are helping to raise awareness, and we know that it works. We've had great response, and my special thanks to Tara with the town of Hempstead for being so good. We went through where were the best locations to put these signs, and I am really grateful again for the partners that help make Balloon Mission possible. Next slide. Another partner is PSENG Long Island. We have a collaborative safety brochure on balloons and electric safety. with some safe balloon practices. It is estimated over 11,000 hours a year are attributed to power outages from foil balloon interaction. Next slide. And this is the highlight of my presentation right here. Our greatest impact was with this past year, Girl Scout Troop 3735 in Levittown, who chose Balloon Mission for their Silver Award project. They joined us last April for April of 2025 for an AMC's beach cleanup. I might have been at Lido, and we were talking all about balloon litter. The impact that this troop had is not only inspiring, but I am so, so proud of them. They did everything. They got 8 balloon bins in Levittown. They did presentations, they did workshops. They did a sticker campaign to weight down your balloons and never let them fly in the sky, say no to sky trash, and save our oceans. They messaged, so if you think about the 2 middle schools that they had, 1,923 students and faculty were exposed to these announcements. They had 2 churches, the Levittown Public Library, Levittown Town Hall, with the support of the town of Hempstead, who actually built a balloon bin based off of the Long Island Children's Museum schematics, and then recognized the troop with citations. I could not be prouder. And this just shows how if we work with our youth, this is their future. And you can take something as simple as balloons and responsible balloon practices and message it out to the community. They've had so much great support. And we just show between collecting 82,000 balloons and this type of collaborative partnership, people really do care about positive change. And next slide. I think the last is just some acknowledgments, and then one more slide is the final one. That's it. We're done.
Okay. All right. Thank you so much, Cynthia. We're going to move to our presentation. I'm sorry, to our question and answer segment. And we have a panel. As I said, it'll be Cynthia, of course, and Dr. Medina and Rob DiGiovanni, and also Rob Weldner. So let me just go back, though. I want to ask some of these questions that are in the chat for Louis Medina. So, Dr. Medina, is the relative abundance of the plastic particles by size related to the varied causes of their formation?
I will say yes to that question. Is a matter of when we talk about fragmentation, those are physical or chemical processes, also biological processes that can produce microplastics. So if the origin of these microplastics are from bigger particles, we can associate that to that process of fragmentation.
Thank you. Also from Stephanie, she said she would assume that the smaller particles are more dangerous because they can infiltrate smaller body tissues. Is that correct?
Yeah, absolutely. So smaller particles, not only for the health of the organism, because they can translocate to the specific organs. They can pass through tissues easily that a big particle. Imagine we're talking about a lot of fish and fish ingestion of plastic. So basically, when you go to the market, you get your fish and your fish are clean. They don't have stomachs. Or if you fish your thing, you take out the stomach. So it's very likely that you're not going to ingest big pieces of particle from the fish. But if those small pieces of plastic can go through the tissues of the stomach and get to the flesh, that is the part that we eat, that can be dangerous. And those are the ones that are very focused in right now, the smaller things.
Okay, that kind of relates to the next question real quick. When plankton plankton ingest the microplastics, do they pass through unchanged to the animal systems, or do the animal systems change them?
That's an excellent question. We don't know. We don't know if there is some process, metabolic process inside the organism that can change the chemistry or the physics of the particles. So we know also that these particles comes with a lot of plasticizers, for example, things that are added to the polymers to make it stronger, to make water resistant, to make it fire resistant. So those are chemicals that we don't know how they interact with our body yet. So that is some part of what it can change the particles. Yeah.
Okay, great. This is a great question too by Christina. If you can identify the type of microplastics, such as the PET water bottle, from its mass and density through vibrational spectrometry, do you think we could eventually analyze the chemical formula of microplastic and connect that piece to a specific manufacturer, such as Coca-Cola, Poland Spring, or something other?
Yeah, I think for that question, I mean, I don't know. I will assume that the specific manufacturer don't make their bottles. There is this company, huge company, that make bottle from
Okay.
them with a specific design. So I don't know if we could relate to a specific company, but we can relate it to a specific manufacturer. One thing that we can do is because plastics are made of fossil fuels. So polypropylene is made of propylene. Propylene is a gas that is made by oil, by fossil fuel. So all these things are chemically unique. So we can measure the isotopes of the carbon that was made on this polymer, and we can relate that isotopic composition in the polymer to specific areas where that petroleum was dig out of the earth. Because the petroleum in the Middle East is different than the petroleum in South America, is different than the petroleum on United States.
Interesting.
So you can relate the isotopic composition of the plastic to a specific origin of the petroleum where this made of.
Okay, that's great to know. Just a quick comment by Dr. Koppelman. Early on, you spoke of plastic production and it's used as cheap. Perhaps we should start saying it's only cheap if you don't consider the environmental and ecological costs. Okay, agreed with that.
It's true.
Okay. Also, Audie's saying they find balloons miles offshore. For those who don't know, Audie is the director of Cresley, and they go miles offshore doing whale watches. If you've gone whale watching off of Montauk, you've been with Dr. Koppelman. He's saying we find balloons miles offshore from Montauk, particularly in high numbers in May and July because it's graduation season. Ay, ay, ay. Okay. How can, Cynthia, how can a community get a balloon bin? James took 3 balloons out of the ocean this weekend at Saltaire.
Yes, we want to get everybody a balloon bin. So you could just email me at Seibold@balloonmission.org, and there are lots of different ways we collaborate. Sometimes if people can't afford a balloon bin, we figure out ways to still collect balloons and keep them out of the environment.
Well, I know Saltaire has a very active sustainability committee, which CC works with a lot. We'd be happy to help you obtain that, just so you know, James. Okay, Christine Suter is asking, whoops, I'm so sorry. There it is. What's the best way to dispose of dirty balloons or balloons found in the wild?
We typically don't put those in the balloon bin because they're dirty and smelly. The balloons that we're collecting are the post-event balloons. So those just go right into a sealed garbage bag.
Thank you.
The dirty ones, yeah.
That's good to know, actually. Braden has a question for Dr. Medina. When you ended your presentation saying you try and contact policy and lawmakers to address these issues, what does that look like? Well, I think the scientists don't, I'm going to answer this one for you, Lewis. I think good science, good common sense, and good advocacy make good policy. So, for instance, groups like Citizens Campaign for the Environment, AMCs, and Operation Splash, we work with a number of the scientists across Long Island, but especially at Stony Brook, at the School of Marine and Atmospheric Scientists, and we use their science to incorporate into policy. And from that, we've crafted legislation and we've done lobbying, and that's how we create bills. But they're always based on good science that good scientists like Lewis provide for us. Let's see what else we have. Okay, Dawn is just letting everyone know that they decorated cardboard boxes and put them in the middle schools in Levittown. That's great. Actually, I think that's really good. Okay. All right. So I'm going to turn it over to Rob Weltner and Rob DiGiovanni for some last words. Rob Weltner, why don't you go first?
Okay. Well, Operation Splash we got our 8 boats out running around. We've got them in around middle of April, around tax day, April 15th. And we have some data collection up to the very beginning of June. And in that short window, a month and a half time, we got about 342 balloons out of the South Shore bays.
That's crazy.
4,323 plastic bottles, 2,118 plastic bags. So when we're talking about, marine debris and plastic, it's the worst scenario it could be. And I know what Dr. Medina was saying, when a lot of the plastic, especially the gallon milk jugs, when they've been out in the sun for a long time, when you go to pick them up, they fracture into a million little pieces, and now you got to pick up all the pieces. And so, like I said, I think education, we're on the right track as far as getting Long Islanders and people to understand that, there are consequences to our trash.
Thank you, Rob. And thank you for all the work Operation Splash does as well. It's amazing how much garbage you guys find in the wetlands on the South Shore. It's just mind-boggling. And your work is not only appreciated, but it's immensely needed. Just so everyone knows, there's no one who's in charge of picking up all the marine debris in these wetlands and in our waterways. And so Rob's organization, which is primarily volunteer-based, has taken upon that challenge for the last several decades. But moving on to Rob DiGiovanni. Rob, the other Rob.
Well, thank you very much. And thank you for putting on this presentation. I think, putting it in perspective, it's these partnerships and all this work that's being done all around the island and making people aware of it is a big factor. Dr. Medina, you're talking about the work that was being done up the Hudson River and the work that you did off the South Shore. And as you're talking about your collection method, I'm just thinking of the whales that we see swimming through work the same way as your collection method does. So whatever we have in the environment is in those animals. And one of the things that AMCs does is we investigate causes of mortality, and we can always, it sounds terrible, we can always dig deeper and find more of this debris and microplastics. And it's just something that we want to work on a lot more diligently, but it's a big challenge. Just because you don't see it doesn't mean it's not there. And that's really what we're trying to get a lot of people to see. And Artie was talking about being offshore. And I remember when I was starting AMCs a decade ago, after many years in Marine Mammal Field, I went out and we were moving a boat from Shinnecock all the way to Hempstead Bay, and in 30 minutes picked up 7 pounds of floating debris that were there. And so it's wherever you are. And as soon as we turned around, then we had a bunch of dolphins swimming by. So we have dramatic impacts on our environments. There was talk about the ribbons and them getting entangled, but it's also, if they ingest them, it's sharp edges. So we really need to think that we have huge impacts on this environment, and anything that we can do to show how much work is being done. Balloon Mission, Cynthia, you do an amazing job with what you do. I'm always impressed. I always feel like we never do enough when I talk to people like you guys. So I think it's great. And if we can figure out how to make people more aware of every one of those cleanups. I mean, Dr. Medina, we're right down on the other side of the bay doing beach cleanups all the time. If we can figure out how to collaborate on those things so that we can spread our resources a lot more effectively, I think that that's really our next step, not just in awareness, but how do we get the most amount of coverage with all the efforts we have. And I think meetings like this and partnerships like this are really a great way. And so I thank Citizens Campaign for bringing it together.
Yeah, and Robbie, can you just mention real quick, we didn't even get to talk about this, but we have to close up here. But when you do the necropsies on whales and dolphins, if you could just mention, do you actually find plastic in their,
Yes.
stomachs?
Actually, it's a really good question. We're always often asked, do you find plastics? And Cynthia mentioned going to the balloons when we were talking about balloon releases, and we do find it, yes. And I remember early on in my career, someone said to me, how many balloons do you find? I said, well, we have a couple that we found. And they went, oh. And I'm like, what number is good for you to find? The number should be 0, right? That's
Right.
what we're looking for. So 1 is bad. That's all we need to know. And we do find it early on. It was a balloon that we found from a political campaign. Of course, once we mentioned that, then the other people wanted to know whose balloon it was. But the reality is the releases were a big problem. It's sad to say that we find marine debris in a majority of the animals that we're able to look at from a sea turtle perspective. We see vessel strikes. So the human impacts are greater. So we are seeing that, and we're doing some diet analysis now on sea turtles, where Kim Dorham is actually working up some of those data, and we hope to have something by the end of the year.
Okay, great. So I want to thank everybody for joining us today. Hopefully you've learned some things. Thank you so much to our presenters, Dr. Louis Medina, Cynthia Seibold, also Rob DiGiovanni, Rob Weltner. We really want to thank everybody for participating, because education does lead to change, and we appreciate you being here for this presentation. We are going to email out the presentations, and there will be a link to the video as well, as some folks asked in the chat. Thank you, everybody, and have a great day.
Thank you. Have a good weekend.